Welcome back. I am Anshu and you are watching Bottleneck. This is the Agenti AI cookbook series where we learn and implement design patterns for AI applications using hands-on example. In our previous video, we discussed about the tool use pattern. We started implementing our tool augmented arithmetic agent. So far, we have created the four Python methods and we used tool annotation to make them a tool for an LLM to understand. This tool is from the LangChain. We created an array of tool. We created tools by name, which is a dictionary which will be used as a lookup by the LLM, and we binded the tools with an LLM. Now, if you missed on my previous video, I will be sharing link in the description. So let's continue. Now for this tool to run, we need our graph. So let's initialize the graph here. Let's import from langgraph dot graph import state graph. Okay, let's create the graph here. Agent builder equals state graph. Okay, now recall from our previous implementation where we used a shared schema with the state graph so that the nodes can communicate among themselves. But here, when we invoke our LLM, say user provides a query. For example, a query could be 2 plus 3 plus 4 plus 5. Now, this may result in a nested structured tool call, which may look like add, add, and again and another add. So here they will have 2 comma 3, then we will have 4, and then we will have 5. Now the tools can repeat multiple times in any order. So our shared state should be smart enough to accommodate all the tool messages. How can we achieve this? The answer to this question is message state, again provided by LangGraph. So let's import the message state. Message state. Okay. Let's add in message state here. Message states. Now, what is a message state? Think of it as a shared whiteboard in a meeting room. Every person in the meeting room writes on the whiteboard when they speak. Okay? Nobody talks directly to each other. They all read from and write to the whiteboard. When the meeting ends, the full conversation is on the whiteboard. In our case, nodes will communicate via message state and all messages are recorded. So how this happens? Let's take a look at the structure of the message state. Message state has two components: list of any message and an add messages. Now list of any messages is a list that grows over time. It holds every message, the user's question, the AI replies, the tool request, tool messages, or the tool results. Okay. It also includes the system message. So everything that we have is incorporated inside the any message. So any kind of message that happens within the AI agent, that will be part of this message state. What is add messages? Add messages is a reducer function. It ensures that the history accumulates the turn by turn automatically. Normally, if you update a variable, the old value is gone because it is managed by a key and value pair. If you remember or recall from our previous implementation, we implemented a shared state as a partial dictionary where we used to implement or append the values or update the values for a given key, but here we want everything, so it will be accumulated or added. The reducer changes this rule. The new messages are always appended, never replacing the old ones. Now why the reducer matters: Without reducer, history is gone. LLM is confused. We will see that in action when we will run our code. With reducer, the history is intact. The agent always has the full context of the memory conversation. Now, the message state reflects the stateful memory. Point to note here is we are passing the entire conversation back to the LLM or the agent that we have. With time, this will grow and this will become another bottleneck for our solution. So we will discuss in detail how to handle the memory or the entire memory management when we will talk about the memory management pattern. All right. Now let's continue with our implementation. Let's add the nodes. Let's add the first node that we have. So we need to invoke the LLM with tools. Let's create dev LLM call. Okay. Again, it will take a state, that is a message state. Okay, and what it will do, so LLM node sends the current conversation with a system prompt to the LLM and returns the assistance response, which may contain the tool call or the response by the AI as a plain text. Okay, so let's note it down. LLM node sends the current conversation with a system prompt to the LLM. Okay, and returns the AI response, which can contain tools or AI message, which may contain tool calls. All right. Now let's define the LLM call. So return. So what it is going to return? As we saw that the message state has the first component as list of any messages. We denote it by messages. The key is messages. If you dig deep into LangChain, you will come to know. Okay, now this messages will be an array of the previous message plus the response that we get from the current LLM invoke. Okay, so it will be LLM with tools dot invoke, which requires a partial dictionary, but here we are going to send an array of message for the AI, and the default will be the message that we are going to send, which will be invoke the last message that will be used by the LLM. How it will be done, we will see in the follow-up node. Okay, so let's add the system message. Okay, now let's import the system message. So what is a system message? System message is a type of message that is used by the AI, by the user, to provide system message. This is not updated by the user. It becomes part of the AI agent and remains there forever until and unless changed. So let's import the system message from langchain dot messages import system message. What else do we have? We have human message and we have tool message. We will need all of them. All right, so these messages we will see in our tool call. Okay, now, so what do we want our system to do? So because we know this system is meant for arithmetic calculation, so we need to provide it that information. So let's add it content Okay, so content would be use tools for all arithmetic calculations. Okay, trust tool results. Exactly. And never recompute. All right. So why we want the LLM to have the tool message as exactly, because if you remember we had tweaked our multiplication method. So in reality, whenever something is multiplied by 0, it will return 0. So LLM will start using its brain, its training knowledge, and it will try to correct the response. But we don't want that. We want LLM to use our tool irrespective of whatever is provided. Okay. Now, the second input that we are going to provide is combine all the intermediate results with further tool calls. Okay, to produce the final response. To produce one final answer. Now, we have to make sure that LLM understands what we need. It has to accumulate all the responses and come up with the final answer. It should not just throw back the tool results that we have, but also perform the operations that is required by the user. All right. Now, we need to append all the previous messages so that the LLM understands what is next and what it has to do, which tool to call, what is done, and accumulate everything together. So let's append the state messages. Okay, state message will grow with time. So we have now our LLM call ready. Okay, so what will happen in this scenario? Once a user invokes the LLM based on a message that we saw an example 2 plus 3 plus 4 plus 5. The LLM will infer the user messages. It will invoke the LLM with tools. This will return either AI response as a text or a tool call. Now tool call will be the series of tools that it need to execute. It will keep on executing those tools and accumulating the response as the tool message. Once all the tools are executed, it will use its intelligence to accumulate the response and come to a final answer. Now in this process, how these tools are being used and what is the role of tool by name. This is what we are going to do with the next node. And that brings us to the end of our part 2 for tool augmented arithmetic agent implementation. In this video, we have implemented the stateful memory with tool use pattern by understanding the core concept. We also saw how reducer is going to work and what is the role of reducer, what happens if there is no reducer. Now, this makes this intelligent tool enabled agent. In the next part, we will bring everything together by completing the line graph workflow. We will create and connect all the required nodes, implement the agent's decision making logic, and see the other design patterns as React and agentic loop working together in the real world application and run the solution end to end. If you found this video helpful, please like, share, and subscribe for more practical insights into AI architecture, agentic systems, and modern design patterns. Thank you for watching, and I will see you in the next video.